Welcome to lecture 6 of AI Simplified series. In this lecture, we are going to talk about one of my favorite topics, which is gated recurrent units. I remember when I learned LSTMs, it looked like very confusing to me. I couldn't quite understand the intuition behind it, but looking at GRUs, things made absolute sense. And GRUs alongside LSTMs, which we covered in lecture 5, are being used to address one of the issues of recurrent neural networks, which is very short memory issue. So they cannot retain memory through time. GRUs are significantly simpler in terms of architecture, and in practice, they're doing almost as good as LSTM. So there are simplified versions of LSTM, and that's what we're going to cover today. Without further ado, let's jump into the numerical example. All right, let's focus on GRUs, or gated recurrent units. This is a simplified version of LSTM. Actually, you're going to see we can get almost a similar result as LSTMs, but with significantly less computation and an easier framework to understand. As we discussed in LSTM case, it wasn't always easy to follow what was going on there. So in the GRU structure and architecture, we have two main concepts. One is forget gate and input gate. We don't have any other thing. We don't have output gate. We either have forget gate or input gate. So one thing that regulates everything is this sigmoid function here, ZT, which tells us how much of the old information we should keep, and 1 minus that is what we are going to add as a new information. Again, as before, GT, which is hyperprolic tangent activation function here, is our main computation. It says, okay, what additional information our new observation is giving us. So that's what is happening here. So this ZT, let's say this ZT becomes 0. Then it says that from the hidden state, bring nothing, update the whole hidden state from the new information that came. If ZT is 1, it will dictate to ignore the whole new information completely and only carry forward the old hidden state. So and another thing you can see in GRUs is you only carry one hidden state. In contrast to LSTM that we had C and H, C for long-term memory, H for short-term. Here we combine the two into one, but we consider both the history and also the new things that are added to it through X. And what is controlling it is this ZT function. Another difference that it does have is an RT function that we have here. This RT function precludes us to input the hidden layer directly to our main G function. So what it does, it passes through R and then multiplied by this H, and that is what is gonna pass through the weight that it has to the G. So this is the only difference that it has. It's a very simple to follow architecture. Again, X, your input is going through both all of the nodes I have Z, R, and G. H is going to get fed directly to R and Z, but indirectly to G through multiplication of whatever the output of this R is here and that one. And ZT tells you what percentage of forget gate we use, and 1 minus that will be what percent of input gate we use. So if it values the previous states more than the current additional information you got, Z becomes close to 1. If it values the new information more, and the information is more exciting, ZT becomes closer to 0. That means it forgets everything that has happened in the past, it updates the weight there. Let's work on the same numerical example that we had. Remember, we had this. We said we have 3/4 of data, 70, 30, and 100. These are the price of barrels of oil in through quarter, let's say 2 quarters ago, a quarter ago, and right now. And based on that, we want to predict whether or not Fed is going to increase the interest rate. So we are going to use the same example with some new numbers. So without further ado, let's move forward to that example. So here I just initialize some weights here. So 0.1 is the weight of H for R. 0.3 is the weight of H for Z. 0.02 is the weight of X for R. 0.04 is the weight of X for Z. 0.05 is the weight for GT. And 0.1 is the weight that comes from the multiplication, whatever RT was, and HT that would be fed to XT. I'm assuming that all of my biases are -1, including the bias of this Y. And like before, for Y, we are going to use a logit function, and we're assuming that WY is equal to 1, and the bias is -1 here. So let's get started. So at the very, very beginning, we do not have any H, because that's the first time that we have. So X1 is 70, and H0 is 0. Sorry, let me change it. H0 is 0. So let's calculate what will come out of RT. So R1 would simply be logit of, remember the blue ones, the blue colored nodes here are all sigmoid function, and this red one is hyperbolic tangent. So that would be logit of 0.1 times whatever H was, which was 0, plus 0.02 times whatever X was, which was 70, plus its bias, and the bias is -1, so plus -1. So if you do that, that will be logit of 2.5, so logit of 0.2 times, that is 1.4, so logit of 0.4, which is 0.598, 0.0598. So here it will be passed. Okay. So now let's look at ZT. ZT would be, I do this only once, and I expect these be natural to you because we have done it many times. So ZT is, it's logit of 0.3 times 0, 0.3 times whatever H was, plus 0.04 times 70, plus its bias. We said the bias everywhere is -1 in this example. So that will be sigmoid of logit function of 1.8. So it's going to create 0.8581. So what it says is that it says keep 0.581%, so 85.81% of whatever state it was. So this is what is passing, 0.8581, and only consider 1 minus that, which is about 14.18% of whatever comes from this G function. So that is an important distinction to know. So this Z is what says, okay, how much of this gate is open, how much of this gate is open. So the more of this gate is open, the less of this one. And this is beautiful because one parameter is controlling both input gate and forget gate there. Okay, so now let's look at the GT function. So GT function would be tangent hyperbolic of, so here we have 0.598. So that should be multiplied by H, which is 0. I intentionally write it so that you see what is happening here. And then it should be multiplied by this weight, which is 0.1. So as you can see, H was indirectly entered here. R is dictating how much of H enters G, plus 70 times 0.05. 0.05 was here. And again, the bias was -1. So that would be, give you 0.9866. So G function is 0.9866 in this case. So the input gate needs to multiply this number by that 14%. So if you do that, so if you multiply these two numbers, what is coming out of it is 0.1399. 0.1399. I hope that you can read that. It's 0.01399. And then, so from here, since 0 is input, 0 times any number is 0. So from that forget gate, 0 comes in. So 0 should be added to 0.1399. So here we have 0.1399 that will be outputted. So H1, the hidden state that goes to the next round, is 1.399. Okay, now we have to calculate y hat. What is the probability that we're gonna see Fed increasing its interest rate? That would be logit of 1 times 0.1399. And we said the bias is -1, so we 29.7%. Very good. So we go to the next stage. So now next, we had a lot of zeros that propagated. So now we have more input. So let's do it again. As you can see, this is significantly easier to follow than what we used to have in LSTMs. And it makes more sense because there's only one gate that controls both forget gate and there's only one value that controls both forget gate and input gate. So anyhow, so now X is 30 and H that was inputted now is 0.1. So I'm not going to get into like too much detail of the calculations again. I just write them down so that if you want to do it yourself, you can do it and verify it. So in this case, RT, which is in this case is R2 because we're in the second round, would be logit of -0.386. That's 0.4. So this is 0.4. So now what we'll have is 0.4 times, because the output of it will be this by 0.1399 times this. So that will be one of the outputs that goes into G plus whatever X is. So now let's look at Z2. That will be logit of 0.241. That would be 0.56. That is saying that keep 0.56 of the old memory and now use 0.44, which is 1 minus that of whatever G is creating for us. And G2 would become hyperbolic tangent of, maybe I just write this 1 down so that you don't get confused. So that would be 0.4 times 0.1 times 0.1 plus 0.05 times xt, which is 30 now, minus 1, which was the bias. That will be tangent hyperbolic of 0.50, which is 0.466. So GT is 0.466. So now we need to multiply these two numbers together. So if you do that, that would be 0.205. And here, if you multiply 0.139 by 0.16, so these two numbers, the forget gate, what we pass through the forget gate is 0.0784. So you add these two, that will be your next H. So your next H that going to get passed to the next step would be 0.0784 plus 205. And that will be, it has a little bit more digits. I use Excel to calculate them. So I just write the whole digit if you want to follow. And y hat 2 would be simply the logit function of what gets imported in it, which is 0.28359 times 1 minus 1. So it's gonna give you 32.8%. So the probability gone a little bit up from the previous case. And now we need to just repeat it for x3 equal to 100, because on this quarter that we are very interested, things were 100, but what we carried was 0.2835 from it. And I just write down the end result. I ask you to write it down yourself, because the best way to retain something is to do it by hand. I promise you, if you do it by hand, you will never forget it. And you should find these numbers for this specific input. And as you see, working with GRUs or gated recurrent units is a significantly easier task than LSTM. LSTM was a mess, in my opinion. It had a lot of connections, probably an unnecessary two states and like C and H that needed to be carried forward. And also you had an output gate that we don't have here. Yeah, so the GRUs are simpler, and in practice, they almost perform the same as LSTM. So the paper that I think was published somewhere in 2013 or 2014, I cannot quite remember, when I think it was in that range, changed the perception about recurrent neural networks, and this cell of GRUs helped a lot because it's easy to understand, it makes sense. Z functions specifically control both gates, makes absolute sense, and computationally an easy task to do. And I hope that you enjoyed this lecture.